Okay, so this is video 4 of Unit 10, and we are going to be covering 14.8, 14.9, and 14.11 in your book. So if you want to read that beforehand, that would be recommended. This first part is going to talk about standing waves. So when a traveling wave reflects back on itself, it creates traveling waves in both directions. And the wave and its reflection interfere according to the superposition principle, which we talked about. So like the wave will interact with its own reflection, and then it will cause either constructive or destructive interference. With exactly the right frequency, the wave will appear to stand still. So this will be called a standing wave. And I will hopefully have a demo to show you in class for that, either on Tuesday, Wednesday, or Thursday, Friday. Okay, so there's this thing called a node, and this occurs when the two traveling waves have the same magnitude of displacement, but the displacements are in opposite directions. So this is like perfect destructive interference, and so basically they'll cancel out, and you'll end up having a net displacement of 0, and the distance between two nodes is going to be 1/2 the wavelength. An antinode occurs when the standing wave vibrates at a maximum amplitude. And I'll show you guys pictures of this so that you can see what it actually looks like. But the antinode is when it has the maximum amplitude. So in this picture, the nodes are these pieces right here, the little spots where it's 0. And the antinodes are these big high pieces. Those are antinodes. If you have waves on a string, you're going to have nodes at the ends of the string because those points are going to be fixed. So you're going to always have nodes on the ends. Okay, so the lowest frequency of vibration is called the fundamental frequency. And then the higher harmonics are positive integer multiples of the fundamental. So you'll have the first harmonic, second harmonic, third harmonic. And you'll notice that it's like the number of nodes that you have, or antinodes, basically. It's more the antinodes because you don't want to count both. So for this first, if you notice, it has one antinode and two nodes, and so this is the first harmonic. In this picture, you have two antinodes, and so this is the second harmonic, and then in the third, you have three antinodes, and that's the third harmonic. And then you can see the length of the string and its relationship to the wavelength is given below in each of these little pictures. It's highly recommended that you draw these pictures when the problem talks about harmonics. And then this is how we relate this to music. And so we'll talk about how this is related to music when we get into class. But you'll use this equation if you wanted to figure out the frequency at any certain harmonic, given the string and the force on the string and the length of it. You have to have positive integer multiples of the fundamental frequency in order to have a harmonic. If it's not a positive integer, then it's not going to give you a harmonic. So this is just a quick slide. You don't need to know too much about this, but basically F1, 2, and 3, so the first three harmonics are going to form a harmonic series. F1 is the fundamental and also the first harmonic. F2 is the second harmonic or the first overtone. And the waves in the string that are not in the harmonic series are quickly dampened out. And so it'll select the standing wave frequencies. Okay, so forced vibrations. A system with a driving force will cause a vibration at the frequency of the driving force. When the frequency of the driving force equals the natural frequency of the system is said to be in resonance. So this is like if I have a string and I kind of shake it up and down, or I vibrate it up and down. The string's frequency will match the frequency of the thing that's oscillating, that's causing the frequency, causing the vibrations. When the vibration has a frequency that matches the natural frequency of the string, so if it has one of the frequencies, either the fundamental or the first harmonic or anything like that, then it's said to be in resonance. And we'll talk about resonance a little bit further. So this is an example of resonance. If pendulum A is set into motion, so if we move pendulum A back and forth, pendulum C will start to oscillate. And it will match the frequency of A. And that's because A and C have the same length of string. And so they're going to be resonating with each other. I'm sure you've heard that word. It resonates with me. It's kind of like it fits with my natural thinking. So this is the same thing. It fits with the natural frequency of this one. And the frequency is dependent on the length. So that's why when the lengths are the same, it'll affect it. These other two might move a little bit, but they definitely won't match the frequency of A. Some other examples of resonance that you guys have seen is a child being pushed on a swing, shattering glass. I'll show you a video on the Tacoma Narrows Bridge collapse. And it basically collapsed because the wind was vibrating the bridge at its natural frequency, and then so the amplitude quickly increased. And then the same thing happened with the Nimitz Freeway collapse during the Loma Prieta earthquake in the 80s. Okay, so beats, and you guys have heard this because that's your headphones, but beats are actually alternations in loudness due to interference. So waves have slightly different frequencies, and the time between constructive and destructive interferences alternates. The beat frequency is going to be equal to the difference in frequency between two sources. So here the beats are shown, so you can see that there's two different waves, and when they are constructive and destructive, they kind of build the shape in part B that you're seeing. So that's these ones added up in part A become part B, and so the loudness increases because of the two frequencies kind of adding together or canceling each other out at different spots. And so that's what causes the beat. Okay, so I want to walk you through this example. It's very similar to one of your homework problems. So it says the high E string on a certain guitar measures 64 centimeters in length and has a fundamental frequency of 329. When a guitarist presses down so that the string is in contact with the first fret, the string is shortened so that it plays an F note that has a frequency of 349. How far is the fret from the nut? Overtones can be produced. So let's do that first part. How far is the fret from the nut? So we're looking here at this picture. We want that little distance from the first fret to the nut of the guitar. So the length of the string is from the bridge to the nut, and so since we're going to press down at the first fret, then we're going to be shortening the length of the string. So we need to figure out by how much is that shortened. And so they gave us the length of the string initially, which was 0.64 meters. And they gave us the fundamental frequency, F1, which is 329. And then they said that the new frequency is 349, and we're trying to figure out the length. So I'm going to go to the next page and show you guys how to do this. Okay, so all I'm going to do is I'm going to plug into the equation for the fundamental frequencies and everything. So this one, the frequency equals n, which is the number of whichever frequency it is. So for frequency, fundamental frequency, n will be 1 over 2 times the length, and then square root of f over mu. So this should be a square root. And so for F1, I know that the frequency is 329 equals 1 over 2 times 0.64 times the square root of f over mu. And so this is going to stay the same since it's the same string. That's going to stay the same for both problems. So I'm going to solve for that using these numbers and then plug it into the next equation. So if I multiply by 2 and I multiply by 0.64 to both sides, I end up with, 421.12 equal to my square root of f over mu. And then if I just keep that and I plug in using this, trying to figure out which frequency this one is, then I'm just going to plug in, let's see here. So this is going to be, and this is the fundamental frequency for f. So this is going to be 349 equals 1 over 2 times the new length times 421.12. And so if I solve for L is going to come out to 0.603 meters. And I started with 0.64, so if I subtract 0.64 minus 0.603, I get the difference in the length, which is going to be 0.037 meters. That's how much it gets shortened by when it changes from the fundamental frequency of E to the fundamental frequency of F. So the next part of this problem wants us to figure out where on the string do we need to press down. So where are the nodes, basically, that we need to press down to hear the second and fourth harmonic. And so we're going to find where the nodes would be on this string for the second harmonic and then for the fourth harmonic. So I'm going to go to the next page. So in order to figure out where it is for the second harmonic, I'm just going to draw a picture of what the second harmonic looks like. So I know that there should be two antinodes. And so if I want to figure out where this node is, so I know it's going to be at, let's see, if this is the whole length, this is the whole length, then I know that my node is at 1/2 of the length. And so that would be equal to 1/2 of 0.64 meters. And so that would be 0.32 meters. So I'd want to press down at 0.32 meters for the second harmonic. For the fourth harmonic now, I'm going to have, let's see, so 1, 2, 3, 4. So I need 4 antinodes. That's why I would suggest drawing it. 4 antinodes, so I know there's a node 1, 2, and 3. There are 3 nodes in there that I can go ahead and need to push down on. So the length of the string is this full thing. So then that means that the nodes are at, let's see, 1, 2, 3, 4. There's 4 pieces, so the node's at 1/4, 2/4, and 3/4. So I have nodes at each of these 3 spots. So then I just need to figure out 1/4 of 0.64, which would be 0.16 meters. Then 1/2 of 0.64 would be 0.32 meters. And 3/4 would be 0.48 meters. So that's where I would need to press down for the 4th harmonic if I wanted to find the nodes at those spots. And that's it. So that's all they wanted you to find was where the nodes are. So that's 1, 2, and 3. And we'll talk a little bit more about this in class so you guys can see it. Okay, let's do one more example. So this is as standing wave vibrations are set up in a crystal goblet with 5 nodes and 5 antinodes equally spaced around the 25 centimeter circumference of its rim. If transverse waves move around the glass at 1,000 meters per second, an opera singer would have to produce a high harmonic with what frequency in order to shatter the glass with resonant vibration? So basically we need to figure out what harmonic or what frequency would this person need to be singing at in order to resonate with the glass. So we need to find a natural mode of frequency for this glass. So if the antinode number is 5, then that means N is 5. We know that the length is 0.25 meters because it said that it was 25 centimeters around. We know the speed is 1,000. So I would draw it. So 5, let's see, so I'd have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there are my, sorry, these are my walls kind of. So there are my 5 pieces. So let's see, if I know that the length is this whole thing, let's see. So 1, 2, here are my nodes. So my wavelength goes from here to here. So let's say I have 2.5 wavelengths for the entire length. So L equals 2.5 times the wavelength, right? So then what that means is we need to solve for the wavelength. So if we know L, which is 0.25, you know, this is 2.5. If we divide, and we get the wavelength is 0.1 meters. And so then, since we have the wavelength, we know this equation. Then one of these natural frequencies is just going to be V, which is 1,000, divided by the wavelength, which is 0.1 times the frequency. So we can divide by 0.1, and our frequency would be 10,000 hertz. So the opera singer would have to sing at 10,000 hertz in order to set up resonant vibration in the goblet. And we'll talk about a little bit more about all these concepts when we come to class. But now would be the time for you to write down your questions on the Google Doc that's on the top of Moodle. So any questions you have about either one of these examples or about any of the concepts in this chapter, I would first read the chapter. It really helps you understand. And then if you still have questions, then go ahead and record them in that Google Doc, and I'll take a look at them before class.